The next step after constructing the datum reference frame for the soft gauge is to actually locate and orient the part feature that we are trying to check versus the geometric tolerance. So, question that we need to address is, first of all, how do we construct that geometric model for a feature? And then how do we relate that to the datum reference frame that we've already constructed? So going back to the previous example where we have datum B and datum A. Datum A, of course, the plane, datum B, the axis of the cylinder corresponding to the half-cylindrical slot. What we need to do is now look at the feature as opposed to the datum reference frame. Now don't forget, when we are locating and orienting the feature, we do not consider the datum reference frame, but we try to figure out where is this smaller slot with respect to our coordinate system, not A and B. So we'll use the same principles again in order to determine where this is positioned and oriented, because we're trying to check the parallelism of that half-cylindrical slot with B. We'll try to find the axis of this cylinder, and then we'll try to relate that axis to our datum reference frame. Well, what if we were checking for cylindricity, to start with a simple case, and we wanted to know how cylindrical that feature is based upon a cylindrical tolerance? The nice thing about a soft gauge is we can determine that. The first step, of course, is to find the axis of the part feature, and that's based on our best fit criteria that we've previously discussed. So we'll select an LP norm estimation method and find the minimum and maximum R based on that fit. The maximum will look through all the R sub i's. If you recall previously, that's the distance from the point to the axis that we find. And then we'll take the difference between those two and see if it is within our tolerance zone width. So in this very simple case, we've fit a cylinder using some type of LP norm estimation. We've determined the maximum and minimum deviations, and then we've used that to tell us something about whether or not it's within a tolerance zone. So in our simple case here, we'll just extend that and add other components in order to determine other types of geometric tolerances. Well, if we want to deal with parallelism, we have to think about our relationship between the feature and datum B. So here in this figure in red, I've indicated the feature that we are trying to determine, and then we've got our axis corresponding to our datum reference frame, and that was previously determined. So we want to look at the relationship between the feature axis and datum B. In order to do that, first of all, we find the datum, which we did previously. Then we find the axis of the part feature, which is the same as finding the datum, except there's no constraint here, right? And then all we have to do is find the distance from the endpoints being over the length of the feature. So I've got D1, one endpoint, the distance from one endpoint, D2, the distance from the other endpoint. And that'll just simply be the difference between the points and the location here on datum B. So I calculate D1 and D2, and similar to what we did with cylindricity, I'll subtract the difference, and the difference essentially will tell us something about our tolerance zone. So if you recall, this axis has to fit within a tolerance zone that's aligned with B. Now we've ensured that because we're taking this distance perpendicular to B, and now if I take the difference, absolute difference between the two, it will be less than or equal to the tolerance zone width if it's within the specification. Now note the tolerance zone width is the diameter here, and so we're comparing this difference between the top and the bottom with our tolerance zone. It doesn't matter where the tolerance zone is located, so we don't take into account the location of the tolerance zone when we determine this difference. An alternative approach, which will give you the same answer but using our trigonometric relationships, is to find the actual angle between the datum and the axis. Well, we already know how to do that using either the dot product or the trigonometric relationship. And then secondly, we need to find the angle, the maximum angle, based upon the tolerance zone specification. So now instead of using the difference in distances, we'll say if the theta that I measure here, and this is the tolerance zone width, t, if the theta that I measure for the actual axis is less than or equal to theta max here, and theta max, of course, will be related to our tolerance zone width and the length of the feature, as you see here. Or we find the width of the deviation, and that is the length times the tangent of theta, and ask is w less than or equal to t. Either way, we should come away with the same conclusion. Now note we have more information than we would with a hard gauge because we actually know what the value of theta is here versus it passed perhaps in the hard gauge, but we have no idea at what angle the feature is oriented. What about location tolerance? What if we were trying to determine whether the location of the feature is within the tolerance zone? Well, the same type of principles will apply. First of all, we find the axis. Again, we don't consider the datums here. And then we want to know, is it within the cylindrical tolerance zone at true position? So now we have to find the distance from true position to the axis. So this is where our datum reference comes into play, and it did not come into play with the parallelism. So if I know the datum axis, similar to what we did before with B, then all I have to do is find the distance from the endpoints to that axis. And so as you can see here, I have a datum axis similar to B, and then I have a tolerance zone that I have centered on B. And now I have my actual axis that I've determined here. Once I do that, then I can take the difference between the points, the endpoints here, and our axis. So I calculate this, which is fairly straightforward, and now I'm going to look at the half width of the tolerance zone. In other words, the dotted lines here indicate how far we are from the axis corresponding to true position. So if that distance, which is a radial distance, is less than the radius of the tolerance zone, then we're going to say it is within tolerance. So you can see a lot of similarities between either cylindricity, parallelism, and location. The differences have to do with the relationship of the datum feature to the tolerances that we are trying to describe in terms of constraining either position and or orientation. And we also saw differences in how we do our comparison to determine whether it's within specification. So you need to understand what the feature model is that you're trying to fit here. Once you determine that feature model, such as a cylinder, then you determine the deviation from that and use your best fit criteria to come up with the best feature model. And then you need to determine your geometric criteria for acceptance based upon the tolerance specification. So once I've identified that geometric model, then I'll have a set of parameters that need to be estimated, similar to what we did with datum features, determine my LP norm criteria for a good fit, go through our optimization procedure to estimate the parameters, and use my acceptance criteria to say whether or not it's within geometric tolerance.